6 minutes ago, a telescope in the mountains of Chile flagged something moving through our solar system that nobody on Earth had ever seen before. And by the time you finish reading this sentence, it will have already flagged several more. This is not an exaggeration for effect. The Vera C Rubin Observatory, the machine that stopped the world back in June with its first images, has now officially begun its real mission. And what it is finding in these opening weeks is stranger, faster, and far more disturbing than anything its first release hinted at. Back when those first images dropped, the public saw dazzling nebulae, distant galaxies, and a handful of freshly discovered asteroids, all captured before the telescope had even finished its calibration process. What almost nobody outside the astronomy community realized was that those images were only a preview, a proof of concept designed to demonstrate the machine worked. The actual survey, the one built to run continuously for an entire decade, had not even started yet. Here is the number that should genuinely unsettle you. In just a month and a half of early optimization observations, before the real 10-year survey had even formally begun, this single telescope discovered over 11,000 asteroids that no human being, no previous telescope, and no prior survey had ever detected. 11,000 new objects in our own solar system found in less time than most people take to finish binge-watching a television series. Now understand what that number actually contains, because it gets worse. Of those 11,000 newly discovered objects, 33 were classified as near-Earth objects, meaning asteroids whose orbits bring them close enough to our planet to matter for planetary defense. 33 previously invisible objects capable of crossing paths with Earth, sitting undetected in the darkness until one machine finally looked in the right direction. Planetary defense researchers have spent years arguing that the greatest danger from asteroids is not the ones scientists already track, but the ones nobody has found yet, objects with orbits that simply never brought them into view of previous, far less powerful survey telescopes. Every one of those 33 near-Earth discoveries is a direct, uncomfortable confirmation of exactly that fear, proof that meaningful gaps in our solar system map have existed this entire time, hiding in plain sight. But that is still not the strangest part. Alongside those near-Earth objects, the telescope also logged 380 trans-Neptunian objects, icy bodies drifting in the frozen outer reaches of the solar system far beyond Neptune, in the same shadowy region where scientists have long suspected a hidden ninth planet might be quietly hiding. Write that again, slowly. 380 new outer solar system objects, cataloged in a matter of weeks, from a mission still technically in its warm-up phase. If a real planet really is out there in that darkness, waiting to be noticed, the odds of it staying hidden just drop dramatically, because the machine, now hunting for it, just proved it can find hundreds of objects in that exact region almost by accident. For over a decade, the search for this hypothetical ninth planet has relied on painstaking analysis of the strange, clustered orbits of a handful of known trans-Neptunian objects, indirect evidence suggesting something massive was tugging on them from a distance. Every new object Rubin adds to that outer solar system catalog gives researchers one more data point to test against that theory. And 380 new additions in a matter of weeks represents more raw material than that entire search effort typically gathered in several years combined. Officials overseeing the project confirmed that the decision to officially begin the 10-year legacy survey of space and time came only after months of careful technical review, examining image quality, system reliability, and calibration accuracy to make absolutely certain the observatory was ready to handle the sheer volume of data about to come flooding in. Now that review is finished, and the real hunt has begun. Before you keep watching, if the idea of a machine quietly rewriting the map of our own solar system within its first few weeks of operation catches your attention, hit subscribe now, because this story is only going to get stranger from here. Here is where it gets genuinely disturbing. Every single night, the observatory now captures roughly 1,000 images of the sky, and its onboard systems compare each new image against everything captured. Before it, instantly flagging anything that moved, brightened, dimmed, or appeared where nothing existed the night before. No human being manually reviews these changes first. Artificial intelligence and machine learning systems process the flood in real time, deciding within minutes which discoveries deserve a closer look. Think about what that actually means. For the first time in the history of astronomy, most discoveries are not being made by a person staring through an eyepiece or squinting at a photograph. They are being made by an algorithm, sorting through more information every single night than most observatories use to collect in an entire year, and then alerting human scientists only after the decision about what matters has already been made by a machine. That shift alone has sparked quiet unease among some researchers, not because the system does not work, but because of how completely it works. An observatory that used to require careful human observation now operates as something closer to an automated surveillance network for the entire visible universe. silently cataloging everything that changes, every single night, without ever needing a human eye to notice first. Scientists involved in building these detection systems have acknowledged the strangeness of the transition themselves, describing a process where their job has shifted from searching for discoveries to reviewing discoveries an algorithm already made on their behalf. Entire categories of objects, faint supernovae, subtle stellar flickers, distant flares, are now being caught, not because a person happened to be looking at the right moment, but because a piece of software never stops looking at all. Now here's the part almost nobody is talking about yet. This telescope is not only built to catalog objects sitting still, it is specifically designed to catch cosmic events at the precise moment they happen, meaning collisions between dead stars, black holes actively feeding on nearby matter, and explosions bright enough to briefly outshine entire galaxies. Scientists call this multi-messenger astronomy, cross-referencing light detected by Rubin against signals like gravitational waves and neutrinos picked up by completely different instruments elsewhere on Earth. That means when a gravitational wave detector somewhere on the planet picks up a ripple in space-time caused by two neutron stars colliding, scientists can now turn to Rubin's nightly data and potentially find the exact flash of light that event produced, sometimes within hours of it happening. A cosmic collision that once might have gone completely unnoticed can now be confirmed, located, and studied almost the moment its light finally reaches Earth. Before this capability existed, matching a gravitational wave detection to its actual source in the sky was often a slow, frustrating process, sometimes taking days or weeks of searching through limited telescope coverage while the visible light from the event steadily faded away. Rubin's constant, rapid scanning of the entire southern sky changes that equation completely, giving researchers a live, continuously updated map to check the instant any other instrument on Earth detects something worth investigating. The implications extend well beyond neutron-star collisions, too. Neutrinos, nearly massless particles capable of passing through entire planets without interacting with anything, occasionally arrive at Earth carrying information about violent events happening across the universe. When a neutrino detector buried deep underground registers a signal, Rubin's archive can now be searched almost instantly for any matching flash of light in that same direction, turning what used to be an isolated particle detection into a fully confirmed cosmic event. Now consider the price tag attached to all of this. The observatory itself cost roughly $800 million to build, funded jointly by the National Science Foundation and the Department of Energy, and it sits perched at an elevation of 8,800 feet atop Cerro Pachon, chosen specifically because the site's dry air and dark skies make it one of the most optimal stargazing locations anywhere on the planet. That figure, $800 million, sounds enormous until you compare it against what the telescope is now producing in return. A single year of Rubin's operation is expected to generate more raw astronomical data than every other telescope on Earth has collected throughout all of recorded history combined. Measured purely by information gathered per dollar spent, almost nothing else in the history of scientific instrumentation comes close to matching it. Jelko Ivezic, the astrophysicist who has led the project for years, explained that the final go-ahead to begin the full 10-year survey was not a simple formality. Every system, from the massive camera to the data pipeline distributing information to researchers worldwide, had to prove it could function reliably under real operating conditions before the observatory was cleared to begin its actual decade-long mission. That mission is now officially underway. And the early numbers suggest that what this telescope produces over the coming decade will not simply refine our understanding of the solar system and the wider universe. It may completely replace the previous one, given how quickly a few weeks of test data has already outpaced discoveries that used to take other observatories years, sometimes entire careers, to accumulate. Researchers, who have waited their entire professional lives for a machine like this to finally exist, describe the current moment as genuinely disorienting, watching decades worth of expected discoveries arrive in a matter of weeks rather than the careers they had originally planned around. Entire subfields of astronomy built on the assumption of scarce, hard-won data are now being forced to adapt to the opposite problem, a genuine abundance nobody fully anticipated arriving this quickly. There is something else worth sitting with here, something almost poetic about the timing. Just months before Rubin's first images stopped the world, a separate observatory detected an interstellar comet, an object that originated entirely outside our solar system, passing silently through our cosmic neighborhood on its way back out into deep space. Rubin's new capabilities mean objects like that, visitors from other star systems, are now far more likely to be caught the moment they arrive, rather than discovered after they have already begun leaving. Interstellar visitors like that remain exceptionally rare in the historical record, with only a handful ever confirmed by any observatory on Earth. Each one offers scientists a genuine physical sample of material formed around a completely different star, chemistry and composition unlike anything native to our own solar system. Every additional night Rubin spends scanning the sky increases the odds that the next interstellar visitor gets spotted early enough for other telescopes worldwide to study it in detail before it disappears back into deep space for good. Now here is the detail that should make you pause. Tony Tyson, the astronomer whose original vision decades ago laid the entire foundation for this observatory, was recently named to a prestigious list recognizing the 100 most influential people currently shaping science and society worldwide. A project that began as one scientist's theoretical proposal has now become a machine capable of rewriting our solar system's map within weeks of switching on. Consider what happens as this pace continues, month after month for the next 10 years. If 11,000 new asteroids, 33 near-Earth objects, and 380 distant icy bodies emerged from just a few weeks of preliminary testing, the true scale of what remains hidden in our own solar system may be larger than anyone previously dared to estimate. Every one of those numbers represents objects that existed silently in the darkness for the entire span of human civilization, completely unnoticed until a single machine on a mountain in Chile finally turned its gaze toward exactly the right patch of sky at exactly the right moment. Now, here is where it gets even stranger. Researchers studying one of the most intensely observed patches of sky in astronomical history, a region known as the cosmos field, recently combined Rubin's newest, deepest images with decades of prior observations from the Hubble Space Telescope, the James Webb Space Telescope, and several other major observatories. Layering Rubin's data onto that existing archive revealed structures and objects in that single patch of sky that none of the earlier missions, despite years of combined observation time, had ever managed to detect on their own. That single overlapping image now stands as one of the most intensively studied regions of the entire observable universe, and Rubin only needed a fraction of its eventual survey time to add meaningful new detail to a data set scientists had already spent decades building. Imagine what the full 10-year survey does to a patch of sky that already took this little effort to reshape. Researchers working on that combined data set describe the experience as almost unsettling in its own right. Watching a single telescope's early, incomplete observations meaningfully improve on work built from 4 separate world-class instruments operating over more than 20 combined years. It was, several noted, a preview of what happens when every remaining patch of the southern sky eventually receives that same treatment across the full length of the 10-year survey. Don't forget to like this video if a telescope quietly rewriting the map of our own solar system within its first few weeks online genuinely surprised you, because most people still have no idea the real mission has even started yet. 10 years remain on the survey, and if the opening weeks are any indication, the pace is not going to slow down. Every clustered orbit, every strange trans-Neptunian object, every unexplained flash of light picked up in coordination with a gravitational wave or neutrino detector somewhere else on the planet adds another thread to a picture of the universe that keeps getting stranger the closer scientists look. 6 minutes from now, this telescope will have completed several more image captures. Its algorithms will have flagged several more unexplained changes in the sky, and somewhere in that fresh data, sitting quietly, unnoticed, might be the exact object scientists have spent decades hoping to finally catch. The world already stopped once for this machine's first images. What it finds next may make that moment look like only the beginning.